Ernest Rutherford's gold foil experiment might be one of my favorites. Rutherford was a student of J.J. Thomson, so they kind of run in the same circles. And here's the setup of his famous gold foil experiment. Ernest Rutherford directed a beam of positively charged particles called alpha particles. And down today we know that alpha particles are actually little helium nuclei. A helium nucleus is like two tiny protons put together with two tiny neutrons. Ooh. So since neutrons are neutral and protons are positive, these little helium nuclei are small positively charged particles. All we need to know at this point is that an alpha particle is positive. It's a tiny little positive particle. And he's going to shoot this beam of positive alpha particles at a very thin sheet of gold foil. So here's my source. Let's say this is my source of alpha particles. Alpha particles can come from things that are radioactive. It's a very common byproduct of things that are very radioactive. Okay, so we got this beam of alpha particles, and we're shooting them at this thin sheet of gold foil. If anybody's ever been like in art, sometimes they'll use gold foil in art. It's kind of like aluminum foil, but it's super, super, super thin. It's kind of the same concept. It's a bunch of gold atoms in a very, very, very thin sheet. And I'm going to add in here too, these alpha particles are positive. So I'm shooting positive particles at this thin sheet of gold foil. Okay, so Thomson's model. Thomson's model kind of ended like this. We've got these little negative electrons scattered throughout our atom. Negative electrons, there we go. And then the rest of the material is just some positive, I don't know, component to the atom. Because I don't really know what it is, but there must be something that's positive in there. To make the atom overall neutral, I did not count my positives and negatives. 1, 2, 3, 4, 5, 6. There's probably somebody that's like, well, that's not neutral. Oh, there it is. Now I have the same number of positives and negatives. Okay, so according to this Thomson plum pudding model, a lot of the atom is just empty space. I mean, you've got these tiny little electrons, but then the rest of the atom is just some positive material. There's a lot of empty space in an atom. So they kind of thought that if we were shooting these really tiny alpha particles, as long as they don't hit an electron, they should pass straight through the gold foil. So I'm an alpha particle, I'm being shot at this very, very thin sheet of gold foil. Boom. What if I land right there? As long as I don't hit an electron, I should zip straight through the atom. It's a lot of empty space. Obviously, if the positive alpha particles somehow like hit an electron, who knows, they might be like attracted to each other, and that could be interesting. But most of the atom is a lot of empty space. So as long as we avoid the electrons, these tiny little alpha particles should pass straight through the gold foil. I'm an alpha particle. I land right there, I should go straight through the foil. And that did happen. Wow. I love these pictures. Okay, so again, here's kind of the Thomson model. Here's kind of that plum pudding model. These are the positive alpha particles. This is trying to show like the track of the positive alpha particles. I'll write that in. Alpha particles. zipping through the atom. This gold foil is very, very, very thin. And as long as we didn't hit an electron, most of those little alpha particles did pass straight through the atom. How do we know? Well, if you kind of go back to this sheet, there was like a magnetic field, this magnetic strip that was placed around the gold foil. So most of these alpha particles really did go straight through, and they hit like right in that area. And so maybe we can say, like, I don't know, 95% of the alpha particles went straight through the foil. Woohoo! Just what we expected. And then all of a sudden it'd be like, whoa, that was a weird one. That one hit in a weird spot. Maybe that was just a fluke. And then, whoa, that one kind of veered off at a goofy angle. Now that's a little strange. Most of the particles really did go right through. But every now and then, they would find a particle detected at a really strange angle. Almost as if it like hit the foil and then like bounced off of something. Okay, so check out this second picture. This is going to be Rutherford. Most of those alpha particles did go right through. So maybe this was like the 95%. That's a 5. That's a weird looking 5. 95%. But that didn't explain the few particles that did bounce off the foil at strange angles. So Rutherford is going to try to explain that. Why were there some of these particles that were deflected at weird angles? And so he starts thinking about these positive alpha particles. Okay, opposites attract, likes repel. So it's almost like my positive alpha particles are hitting something that must also have a positive charge. Or be positively charged. And so then he said, well, maybe I can just tweak Thomson's model a little bit. Most of the space in an atom must really just be kind of this like blank space. He's not going to disagree with Thomson on that. There's a lot of blank space in an atom. I'm still cool with that today. But instead of like this positive charge just being randomly dispersed throughout the atom, what if all that positive material was condensed into like a positive core? Because now that would explain some of these little alpha particles. Again, these are all like the positive alpha particles. If a positive alpha particle hit another positively charged particle, they would repel. And so then, like, depending on exactly where the alpha particle hit, that would determine the angle of deflection. So here they might hit and bounce off at different angles. Like charges would repel. So maybe all the positive material is like this compact core or center of the atom. Like this dense positive core. Because these little tiny alpha particles are hitting something substantial. And that's what's causing them to bounce off at weird angles. This new model, this Rutherford model, also explains why 95% of the alpha particles still went straight through the foil. And as long as you don't hit the nucleus, then those alpha particles should go right through the atom. The only ones that are deflecting at weird angles are the alpha particles that are hitting the nucleus. Rutherford is credited with the discovery of the nucleus. In Latin, it means little nut. Oh, how adorable. So all we did was take the original model from Thomson and tweak it a little bit. He actually still has the electrons just kind of randomly flying around the nucleus. And again, we don't believe that today, so if you're a little uncomfortable with that, it's all right, we'll fix it. He's got these electrons scattered around the outside of the atom. I do like that. The electrons should be on the outside. And then all the positive material is condensed into the core of the atom. We're going to call that positive core a nucleus, meaning little nut. One of my favorite old-time experiments. Rutherford's gold foil experiment that discovered the nucleus.